Hello, my name is Andrew Geary, and welcome to Seismic Sound Off, in-depth conversations in applied geophysics. In this episode, we showcase Johan Robertsson's upcoming virtual course on generalized sampling and gradiometry. Johan spotlights the importance of mathematician Harry Nyquist to geophysics, explains the increased interest in rotational seismology, what geophysicists can learn from seismic data acquisition on Mars, and shares important advice for anyone seeking to succeed in geophysics. To register for his upcoming virtual course on April 20th or May 5th, visit seg.org/podcast. Dr. Robertsson is a professor at ETH, where he holds the Chair of Applied Geophysics and leads the Exploration and Environmental Geophysics group. In 2015, he received the E&I New Frontiers in Hydrocarbons Upstream Award, together with former colleagues from Schlumberger, and also received EAGE's Conrad Schlumberger Award. See the episode show notes for his full bio. Now for our conversation. Speaking of the virtual course, we'll start there. You were given the honor to serve as the 2020 honorary lecturer in Europe on behalf of SEG. Your lecture is called Generalized Sampling and Gradiometry, Changing the Rules of the Information Game course. While you were not able to continue in-person events, you've generously offered 2 free virtual courses based on this topic. So what can attendees expect at this virtual course?
So I start with a review of how the theory of transfer of information was developed almost 100 years ago at Bell Labs in the US. For geophysicists, this is particularly important as it governs how we sample signals when we move from the real continuous world into the discretized or sampled world. And although I think almost all geophysicists are deeply familiar with Nyquist's channel sampling theorem and what happens if we violate that, the story that I'm telling is about important extensions that are not that well known, and that is what I refer to as generalized sampling. So in a nutshell, generalized sampling states that provided that data with the same information content are required, the rules for how the data are sampled can be different. And I describe my lectures around 4 different examples where this has a really significant impact. The first one has to do with spatial sampling requirements. Secondly, with simultaneous source acquisition. And the third aspect has to do with telemetry and transfer of data. The concepts are not difficult to understand, but are extremely important to be aware of. And my hope is that attendees will walk away from my lecture having learned what generalized sampling is and have seen the impact of when this can be important.
Well, let's talk a little bit more about generalized sampling that you mentioned there and Harry Nyquist. What is the importance of Harry Nyquist to geophysics specifically?
Yeah, so the inspiration of my lecture actually comes from the fact that Harry Nyquist, he was born in Sweden, and he grew up in the same rural area that I come from. It's a part called Värmland. He is not at all well known in Värmland, but of course among scientists and engineers he's extremely well known. So Nyquist, he started working at Bell Labs in 1917, straight after finishing a Ph.D. at Yale University. And Bell Labs then, that was a real powerhouse for driving research with a number of really outstanding scientists that made milestone contributions. And it served as a role model for industry-based research in the last century, with lots of the large corporations trying to mimic the success of Bell Labs R&D. So in our industry, companies such as Shell, BP, and Schlumberger, and many others, they all set up fundamental corporate research centers in the first half of the 20th century, very much inspired by Bell Labs. So Nyquist joined Bell Labs in its early days, and he worked on a number of important topics. Among other things, he invented the first fax machine. But Bell Telephone Company, they were also interested in understanding the limits of transmitting information over telegraph lines. And that led him to develop a theory which unified the transmission of Morse signals, which were discrete, with continuous waveforms. And what he did is that he chopped up waveforms into discrete countable pieces, and that let him develop a framework around how this should be done. And for geophysicists, again, this is really fundamental as we move from an analog world to a sampled, discretized world.
Well, now, 50 years later, there's another important person adding to this conversation. So what did Papoulis add to this conversation today?
So he wrote a paper where he described something called generalized sampling. Now, these principles, they were actually known, well, perhaps not entirely, but some of the basic principles were known already at the time when, let's say, a rigorous framework for the sampling theorems were written down in the 40s and 50s. But what Papoulis did was to explain that sampling of signals can be described by linear algebra, so that you can essentially resolve as many unknowns as you have independent equations. So to give you an example, if we measure different linearly independent quantities at the same sampling points, the distance between sampling points can be reduced accordingly. And this is the key aspect that is so important in the applications that I'm talking about. So for instance, if you're in a marine seismic setting and you record hydrophone data or pressure data, if you in addition record pressure gradient data, so the spatial gradient of pressure, you have two linearly independent quantities, and that means that the sampling criteria reduces by a factor 2, so you can be twice as sparsely sampled. And that's nicely and rigorously described in Papoulis' paper.
So now there is an increased interest in rotational seismology. So why the recent interest in rotational seismology?
So that's been an area where people have been interested in for a couple of decades. So it started off with people in earthquake engineering that wanted to test integrity of buildings, for instance, due to earthquakes. So measuring the rotational motion is key there. Then earthquake seismologists have been interested, and there is a group under Heiner Eagle in Munich that have developed and installed a large ring laser that can very accurately measure rotation wave field of seismic waves. In our industry, there are companies such as Schlumberger and IX Blue that have developed rotational sensors. And there are a couple of different reasons for why you want to do that. So the first one has to do with what we could call, let's say, sparse acquisition, where these new sensors enable array-like processing with a single recording station. So for instance, under a single arrival assumption, if you have a measure of rotation in addition to the wave field itself, you can estimate phase velocities, you can estimate directions of arrivals, and that's extremely useful in processing. You can also isolate ground roll in land seismic applications because they really stand out. The second area of applications is what I alluded to earlier, and that is reconstruction of sparsely sampled data. So when we have multiple measurements like this, we can use a sparsely spaced recording station and reconstruct the wave field in between. And then a third area has to do with wave field separation, and that, for instance, has to do with identifying what parts of the wave field are upgoing or downgoing and what parts are PS waves or Rayleigh waves or love waves. And that's also very important. So those are kind of three major areas where this is key.
So in this particular lecture, you even leave the Earth. So why do you talk about the Moon and Mars in this lecture?
So the story from the Moon, that's something that a former PhD student in my group at ETH did. His name is David Solberger. And he used a data set acquired on the Apollo 17 mission, which consisted of 4 densely spaced geophones. When I say densely here, those stations were about 50, 60 meters apart. He then realized that he can use finite difference approximations here to compute various attributes based, for instance, on rotational seismology. And from these attributes, he could derive the first shallow shear wave profile and Poisson's ratio profile of the shallow lunar crust. And that's, I think, a really amazing result. So nobody has been able to do this before him. It's data that is close to 50 years old. And when you just look at these data, they look horrible. It's there's so much scattering, so energy just bounces back and forth. But once you look at the data in this way, the structure jumps out at you, and you can interpret it. And then, yeah, you're right. We also went to Mars. So in January 2019, the NASA InSight mission started to record seismic data from Mars, and ETH has been one of the partners in that mission as well. And the story there is more directly related to generalized sampling, because the whole system, the InSight recording system, was designed to record low-frequency Mars quakes. Because telemetry and data transmission is quite restricted from Mars, certain limits were set about what data rates can be transmitted back to Earth. Now, in a particular experiment there, we are interested in getting access to higher frequency data to resolve the shallow Martian crust. And what we did there was that we realized that we could use generalized sampling to first deliberately alias data, and then take those data, use concepts from generalized sampling, and reconstruct the full data bandwidth. So that's the second example.
And you sort of get at some lessons from seismic data acquisition there, but are there any additional lessons on seismic data acquisition on the Moon and Mars for geophysicists that are working here on the Earth?
So there are a couple of situations where these concepts can be very useful. The first one is if we have a situation where we have multiple signals that interfere with each other, such as in simultaneous source acquisition, then we can use concepts here to separate the responses from the individual sources. Secondly, as we saw in the InSight example, we have cases where we have limited data transmissions or telemetry problems. For instance, if you have a borehole tool in a borehole, then these concepts are useful. And the third one has to do with when acquisition is constrained by logistics. For instance, in deep ocean seabed nodes, then we can make use out of these concepts to extract much more value out of the data.
Now you were able to present your full lecture at several stops before you had to stop and be taken off the road. What did you learn from the participants at these lectures that added to your own understanding of this topic? So
I did learn many things. Let's see what comes to mind in particular is that there is something called prolate spheroidal basis functions, which was also developed at Bell Labs and which features in my lecture that I was not particularly aware of earlier. But they are used to solve problems in Earth and planetary magnetism. So that was really interesting to learn. And while I visited Freie University in Berlin, there were a number of Russian scientists in the audience. And I learned that in Russia, they actually don't refer to the sampling theorem as the Nyquist-Shannon sampling theorem. Because, of course, there was a Russian that also did early work. And his name is Vladimir Kotelnikov. And he published a sampling theory in 1933. He was working on radio communication. But I know that Harry Nyquist published his first work in 1927. So I'm happy to say that Nyquist from Värmland was a little bit earlier still.
What particularly excites you about the future of this topic?
Yeah, so it's you think that there can't be much more to discover. People have been working on these topics for years, decades. But I think that there is yet another level to bring this, let's say, seismic data acquisition up to. And there are new sensors that are under development that is going to enable exploiting these concepts on a broader scale. And I'm particularly excited about applications in exploration seismic, such as simultaneous source acquisition. In earthquake seismology, I think this will have a significant impact on separation of various modes in the recorded seismograms. And in geophysical experimentation in future space missions, their logistics and freight weight is absolutely mission critical. So these concepts are fundamental to exploit and understand to the maximum potential. to give you one example there, at my university, ETH, we are involved in the development of a space-based observatory for gravitational waves. It is going to launch in a little bit more than 10 years' time. And this can, in some sense, be thought of as a giant seismometer. And that's one context where generalized sampling may very well play an important role, very important role to think about.
Well, I get the privilege to speak to amazing scientists on here regularly. And I just want to ask some two general questions that I like to ask of these amazing people. And you yourself, you've mentioned ETH several times. You're Chair of Applied Geophysics there. You've received an award from Schlumberger. You received the EAGE's Conrad Schlumberger Award. Just a few of your honors and accomplishments. What one piece of advice would you offer to someone looking to succeed in your field?
I think it is important to change things, change environment. I benefited hugely from working in Schlumberger, and I spent 15 years there. But I also think that at one point it's good to completely change context, and that's benefited me quite a lot. And I say what I tell young people who are about to start their careers, particularly if they're inclined to be being interested in science and potentially at some point in the future being interested in working in academia, it's very important to look after yourself and look after your CV, publish papers, make sure that you think about yourself and where do you want to be 10 years from now.
Good advice there. And if you could solve just one mystery as a geoscientist, what would you solve?
Wow, let's see.
Only get one.
Only one.
But you can solve it.
I can solve it, okay. Well, I don't know that it's a geoscientist, but I am very intrigued about what gravitational waves can tell us about the universe. And this is like looking at the universe with a completely different pair of eyes. It's an entirely different physics. And that to me is quite exciting. It's things that are happening right now. For the first time, people have been able to observe gravitational waves. It's an exciting area to look at least. We'll see.
Well, good luck it's a couple of weeks coming up, so good luck at your course. And thank you again for dealing with all these little issues with Zoom and the other. And thank you for your time today.
I'm very happy to do that.
Thank you for listening to SEG's flagship podcast. Please share this episode with a friend, colleague, or manager that would enjoy hearing this episode. Your recommendation is the single best action you can take on behalf of SEG's podcast. Go to our website at seg.org/podcast to find all our episodes and learn how you can listen to this podcast directly on your phone without downloading an app. Original music by Zach Bridges. This episode was hosted, edited, and produced by me, Andrew Geary. The SEG podcast team is Jennifer Crockett, Allie McGinnis, and Mick Sweeney. Thank you for listening. This is Seismic Sound Off, signaling off.